Hello, everyone, and welcome back. We have Gaurav Menghani, a staff software engineer from Google Research, to share his presentation with you all. Gaurav, welcome to our stage.
Thank you. Hey, folks, my name is Gaurav. I'm from the Google Research team, and I'll be talking about efficient deep learning today. This is a very quick talk, so I hope to motivate the problem at least and give you a flavor of the techniques that we can use for efficient deep learning and some key takeaways. Please feel free to reach out to me either via Twitter or through LinkedIn or through the Q&A section here, and I'll be happy to answer any questions or have any follow-ups. To start off, I want to acknowledge the stellar work that is being done in the industry and academia in this field, and I'm merely presenting on their behalf. So thanks, everyone. And I would also like to thank my team, Learn to Compress, and the leadership back at Google Research for the support over the years in this work, basically. So here's a rough agenda of the talk. We'll start by covering why we should care about efficiency in deep learning and quickly build from there. So let's start with what exactly do we mean by efficiency? So the naive definition is to get more returns for the same inputs. However, in the context of deep learning models, though, we are learning for a model which, when compared to the baseline model, is either improving on the quality, that means like accuracy, precision, recall, F1 score, and so on, while keeping the footprint of the model, let's say like size, latency, RAM consumption, etc., the same. Or it lowers the footprint while keeping the same quality, or it does both. That will be great if we can improve both quality and lower the footprint. That would be awesome to have. So a model is said to be efficient if it's improving in either of these dimensions while keeping the other constant, hopefully. And now, why should we care about efficiency? First of all, the big news I think a lot of us are aware is that research community does not necessarily optimize for production all the time. That means if you're trying to train or deploy the models that are showing up in papers on archive, they might not necessarily scale for your use case. As seen by the graphs on the right hand side, the number of parameters of state of the art vision and language models has been rising rapidly. So it's very hard to sustain training large models like these, for example, GPT-3, which costs millions of dollars to train. Also, with new applications which are being run directly on device, for example, like Face ID, we cannot just use off-the-shelf models. We have to pay attention to whether or not these models can be run on these devices like smartphones, where you don't have that much compute or capacity as compared to server side. Then there's also this problem of limited label data. Data is, as you know, hard to collect and expensive to label. So it will be great if we can have models that achieve good quality with a small amount of limited label data. Also, for new applications, there might be novel constraints. So the off-the-shelf models cannot necessarily work directly for you. For example, it's not possible to put a full-blown BERT model in, let's say, Google Search's critical path. So that will really kill the user experience. Now let's get to the crux of the talk. How do we make models more efficient? But before we do that, let's take a look at which metrics should we care about. As I mentioned, we have quality metrics on the left-hand side, like accuracy, precision, recall, F1, AUC, etc. On the other hand, we have footprint metrics, like model size, latency, RAM, etc. These two metrics are kind of at odds with each other. You can trade off some quality to get improvement in footprint by naively compressing your model. You can also trade off some footprint to get better quality. That means increasing the number of parameters, number of layers, and so on. In this talk, we'll try to go over techniques where we improve hopefully both quality and footprint without hurting other metrics as much as possible. So let's start with a mental model of efficiency. And this is a non-exhaustive thing. So we've broken it down into four kind of techniques roughly that can be used independently or together with each other. For example, we have compression techniques, which can be used to compress part of the model's graph, such as the weight matrices. Then we have learning techniques, which can be used for training the model with a better loss function that improves its quality. We have efficient architectures, which are layers and models which have been designed to be efficient from scratch. And finally, we have automation, where you can automatically search for efficient models and perhaps learn to combine these three techniques in an automated fashion. And we'll cover each of them in detail. So let's start with compression techniques. As mentioned earlier, these are general methods for compressing a part of your model by reducing redundancy, often at the matrix level. Formally, we can treat it as a model F with some parameters theta, such that we're trying to learn a smaller representation theta prime, where the output of the model doesn't change too much. These techniques typically improve footprint metrics because you learn smaller theta prime while trading off some model quality. A big example is quantization, which is really popular, which tries to map the 32-bit floating point weights into lower precision fixed point values. This is done by linearly extrapolating the range of the weights that you have in your weight matrix to fit in a valid integer range. Typically, in production, we use 8-bit integers for quantization, and this can help compress model weights by 4x. While this is a lossy compression method, it's also possible to simulate this conversion in training, so the model learns to respect this behavior. In fact, multiple papers have reported when you simulate this quantization during training, we get nearly no quality loss. We also get a 2x speed up in addition to the 4x compression because we're using integer operations there. Quantization is now widely supported in both TensorFlow and PyTorch, so you can use it for deploying your models directly on device like smartphones or smartwatches and IoT devices and so on. Yet another common technique is pruning, where the network is like sparsified by removing weights which are not important to the network. This idea is not new. It was pioneered by Jan LeCun back in 1989 with his optimal brain damage paper. There's also a simple implementation which tries to train the model to a certain accuracy and then removes all the weights that are below a certain threshold T. And this is done repetitively until you reach the level of sparsity that you want. Alternatively, you can also use the partial derivatives of the weights with respect to the loss function to decide whether or not to prune a particular weight. If you do this pruning of the weight matrices in a structured fashion, that means you have blocks that are removed. For example, on the right hand side, you can see this diagram where like the gray cells represent weights which have been removed. So if this is done in this blockwise fashion, then you can leverage libraries like XNNPack, which demonstrate a 3 to 4.8x speed up while substantially reducing the number of parameters. And in some cases, there is no accuracy drop, and in others, you can have a tiny accuracy drop if that's a reasonable trade-off for you. Similarly, NVIDIA's latest A100 GPUs support sparsity and pruning with a 2x speed up using 50% block sparsity. There are also other compression techniques that can be used in addition to the previous ones, such as k-means clustering, low-rank decomposition, and so on. And these are easy to use and ready to use in libraries like Matrix Compression Library, and you can use this in the ML framework of your choice. Now let's take a look at some of the learning techniques. These are training time methods that can be used to augment or replace the traditional supervised learning regime. They can be used to improve model quality without impacting the model's footprint during inference. So what you're doing is you're changing the loss function or the objective, so it really doesn't show up when you're deploying these models. So you can use these for improving quality like accuracy, F1 score, and so on. A popular technique is distillation, which was introduced by Jeff Hinton and his collaborators back in 2015. It involves using a large teacher model that you're not going to deploy, but it is used to generate soft labels, which are probabilities for the classes. So rather than using a binary label in the ground truth, we use the larger model to generate these pseudo labels. And then we train a smaller model that you want to deploy to copy these probabilities. The intuition is that the software labels allow the model to learn how wrong or right the predictions are. For example, if given an image of a truck, if the model says it's a car, that's a smaller mistake than saying it's an apple. So whereas if you are using just the binary ground truth data, then you will be penalized for all the mistakes in the same way, which is clearly not the right thing to do here. The following diagram shows how it's implemented. So you have the teacher network and you have the student network. The teacher model is frozen and generates the soft labels for the same input. And the student model learns to optimize for both the regular cross entropy loss with the ground truth data and the distillation loss, which is nothing but the same cross entropy loss with the soft labels. Distillation is also studied and known to improve model accuracy significantly. In the original paper, an ensemble of 10 models was replaced by a single model using distillation. Similarly, we also have impressive results for both BERT-like settings and CFAR10 datasets also. It's also possible to pseudo-label an unlabeled dataset using a teacher model and then use this pseudo-labels in place of or in addition to the large labeled dataset. A paper by FBAI Research demonstrated state-of-the-art performance on ImageNet by pseudo-labeling billions of Instagram images. And it's also helpful when you don't have the original data set. So there are like various combinations you can use distillation in. Then we come to data augmentation, which is another common training time learning technique, which can be used for improving model generalization. In this case, we apply input transformation such that the label can be easily computed. For example, if you have an image of an animal, slightly rotating it should still classify that image as belonging to an animal. So if you make the model learn all these transformations where you don't change the class or you know the class beforehand, it'll learn a better representation with the same amount of label data. As mentioned earlier, these techniques don't impact inference footprint since they just improve the final model quality. So it's quite transparent when you deploy this. It is commonly applied for vision models. A lot of us have been using this for training ML models, specifically for vision in the past, and there have been decent accuracy improvements. However, there are like different policies for NLP and speech as well, which aim to do the same thing, and they work on similar basic principles that you can compute the labels easily from the same label data. So there would be some transformations where doing translation or you're warping the input and so on, but the label doesn't change, or you can easily compute the label somehow. There are also other techniques like self-supervised learning, which is a field in itself. It consists of tasks where we try to learn representations from unlabeled data. One of the examples is the masked language model task in BERT, where part of the sentence is hidden and the model is pre-trained to predict what exactly is that masked part. And once the pre-training is complete on this large unlabeled data set, then the model is fine-tuned to work on the actual task it is used for. So this is well known to be like an efficient technique for training the models when you have very limited data. Now, let's take a look at efficient layers and models. So these are layers and models that have been designed with efficiency in mind. So typically they solve a specific problem with standard architectures. And if you apply this to your problem, they can basically be dropped in directly to use as building blocks. So let's give an example here. There are many, but I'll go over some from the NLP space. A common source of concern in NLP models is large embedding tables. So when you have very large vocabularies and they're beyond a reasonable number, like if they could grow into millions and 10 millions and so on, the proposed way to get around is this feature hashing method. So one of the surprising techniques that works here is if you want to keep a small embedding table, what you can do is keep it limited and learn a shared embedding for multiple tokens. So many tokens can map to the same embedding vectors. So this is not exactly the same as originally where you have one embedding vector per token, but instead you learn this shared embedding. And how you share this is via hashing. So the input is hashed, and then you do modulo the vocabulary size, and that maps to a particular vector in the table. And this surprisingly works in many cases. When you have a simple, let's say, text classification problem, this seems to work very well. Then there's this other approach which goes one step further, projection nets, which tries to use locality sensitive hashing to directly use the random hashes as feature vectors. Naturally, this is not as great as like keeping the full blown embedding table, but it might be okay if the space of the embedding table is a big concern for your model. Now, going to the application of these layers in full-blown models, CLD3 is like a model which uses the hashing trick I mentioned earlier, and it can be used for simple language tasks like language detection, and it does it really fast and within a millisecond on actual devices like smartphones and so on. Similarly, PQRNN is another approach based on projections that I mentioned earlier, and it compares favorably with BERT on certain classification tasks, even though it's like 300x smaller. So let's move on to automation. What do we mean by automation? Automation can be helpful when we want to reduce like some of the tedious work of manual tuning. And it's useful when you want to not just save time, but you also want to reduce the bias. So when we try to construct models on our own or do some tuning on our own, there might be some biases that we introduce during that process. So this way, the automation can help reduce both the footprint as well as improve quality. However, the trade-off is because we are delegating this work to machines, it has to consume some amount of computational resources. So we have to keep that in mind while using automation. Let's start with giving an example. So hyperparameter optimization is very commonly used for manually tweaking the hyperparams to get better results. So I don't need to motivate its importance. Almost everybody has done it. But it might be useful to do this in an automated fashion where we systematically search for better hyperparams. And there are many algorithms for this, ranging from grid search to random search to all the way to evolutionary techniques. I'll quickly give some examples here as well. So one of them is Bayesian optimization, which tries to allocate the search budget in the region of hyperparameters which seem very promising. So instead of doing it randomly, it tries to find out where exactly does it see that we can optimize the objective the best. Then there are population-based training techniques also from DeepMind, which is similar to genetic algorithms, and it does a similar approach, but it tries to do it via evolutionary techniques. Finally, these algorithms are also available in ready-to-use toolkits, either via cloud APIs through Google Cloud, AWS, and so on, or as offline tools also, which you can run, in Colab and so on, using the framework of your choice. Neural architecture search is yet another popular automation technique. So we can think of it as an advanced HPO technique where we're trying to learn or search for hyperparameters that change the model architecture itself. And one of the seminal works in this area is from Barrett, Zoff, and Coakley, who used RL to generate candidate networks, which are then evaluated. So the way we use hyperparameters and then evaluate the performance of the network with those hyperparameters, in this case, we generate whole networks by themselves and which are evaluated separately. Uh, and this was quite expensive, though. It used about 800 GPUs over 28 days. However, one of these follow-up approaches, even though it sped it up by 7x, it was still expensive to train, but it did beat the CFAR 10 state-of-the-art accuracy. And this is how it roughly looks. So you have a controller unit that knows the search space, basically which models and which layers to try out. And it contains the algorithm on how to do this search. So like random search or maybe Bayesian optimization and so on. It is used for then generating the candidates, which are then evaluated separately. And based on the evaluation, this controller then receives a feedback as to how good these models are. If these models are good, then it will keep on searching in that direction. If not, then it will make the necessary changes to generate better candidates in the future. It's also possible to tune both latency and accuracy together, or for that matter, any multiple objectives. In this case, MNASNet, a paper from Google, demonstrated that you can actually find models which are good for both accuracy and latency by, in the evaluation process, using the network and measuring it on a real device, and then using a compound objective and searching for like a model which optimizes for both these metrics together. Now let's connect all this together. As we mentioned earlier, we're trying to find techniques which can improve both quality and footprint. For improving quality without hurting footprint, we can use distillation, data augmentation, or learning techniques. We can also do hyperparameter tuning and architecture search. For improving footprint, we can use quantization, as I mentioned, low rank approximation, architecture, etc. You can also be slightly more aggressive. If you are okay with losing some quality, you can be a little bit more aggressive and try maybe like 4-bit quantization, which does drop some quality, or maybe try like 90% sparsity and so on. Now, I would like to end the talk with some quick takeaways. Firstly, efficiency is critical in deep learning models in production, so we need to give a thought about it when we're training and deploying these models. It can be measured in footprint and quality metrics, and you have to pick the trade-off that works for you. Not everything would have the same, not every problem would have the same trade-off, so you have to make those decisions. And once you make that decision, then you can decide based on the mental model we provided as to which efficiency techniques work for you. For example, if you were looking to improve footprint, an easy way to do it would be through quantization, which gives you a 4x reduction in size and 2x speed up approximately straight up without any quality loss. If you want to improve quality, though, distillation and data augmentation are your best bets, along with self-supervised learning, perhaps. And you can trade off this quality for better footprint if needed. So you can have like a better quality and then maybe combine it with compression techniques to get maybe trade off some of these quality wins for a better footprint. There are also efficient models and layers which have been designed with efficiency in mind as building blocks for certain problems. So we should pay attention to them and maybe use them as baseline or at least as one of the candidates for solving the tasks. And if you have the resources, automation is great to try. You can try to automate HPO if you can. It's relatively cheap. Systematic searches obviously do better than manual tweaking, so go try it if you have resources. If you have an even larger budget, architecture search might also be worth trying out for your problems. With that, we come to an end. I know this was a really quick talk. I wanted to give more details, but I hope I was able to at least motivate the problem and give a few potential solution. The topic is very vast, so please watch out for our upcoming work. There's a book coming up with Manning Publications, and there's also a survey paper coming up, which hopefully will give you more insights into this topic, and it should be on archive pretty soon. And with that, thank you.
Thank you, Gaurav. Fantastic presentation. We have a couple of questions from the audience. Here's the first one. Based on my understanding, one of the attractive features in Feast, beside time travel capability, is the ability to sync offline features used for training with features used for online model serving. It is built for ML domain. Feast can sit on existing data lake, such as BigQuery.
I think this is for the previous presentation, perhaps.
Perhaps. I'm not quite sure. They didn't give me a speaker name. The other one is addressed to Mary. So currently no questions are in the queue. We'll sort of stand by here. I believe this may be for you. Can you explain switch out a little more, please?
Yeah, sure. So, switch out was one of the data augmentation techniques. I'll quickly present that slide first. So switch out, what it does is like it replaces random words in the target vocabulary. So let's say you have a sentence, it tries to, and let's say it's in English. So it might, and you have a sentence which is let's say 20 words. So it'll randomly replace a specific, like a random word in that sentence with some other word from the same vocabulary. And let's say if you were trying to get sentiment classification for that sentence, so that should ideally not change the label. If you have a really long positively sentiment sort of sentence, then changing one word should not change the sentiment. So that is designed for that sort of purpose where the meaning of the sentence is not changing too much, but you're trying to train the model to learn a better representation for that task.
Thank you, Gaurav. Any more questions? Please submit them in the Q&A or the chat for Gaurav. We have 2 minutes remaining on this session. And then we'll have next up, Patrick Hall will begin at 9:30. Gaurav, you may want to keep your eye on the chat and on stage chat. We are seeing questions submitted even after a speaker has completed. Great. Anyone else? Any questions for Gaurav?
Feel free to connect with me on Twitter if you want, or on LinkedIn. I'll be happy to follow up this offline as well.
Terrific. Well, then why don't we wrap up here, Gaurav, and you can just keep an eye on the backstage chat and you can answer folks that are coming through. And we thank you very much for a fantastic presentation. And everyone, we will be back at 9:30 with Patrick Hall and the next presentation session. Thank you, Gaurav.
Thank you. Bye.
Bye-bye.